Is Matthew's bit done?
Oh, we're live. Huh?
Is Matthew's bit
Yeah,
done?
yeah, it's done.
Yay.
I love
Have
how
I-
we're just checking this exactly when the event starts.
Yeah. Yeah, we should be.
Does this have
Give it
does
a
this
give it a
have
check.
code?
Yeah. About that, I was just gonna switch to like
Online GDP?
yeah online GDP.
Yeah, okay, great.
I'm dyslexic. Okay. Do you need any? I'll write some stuff for you already.
What are you doing? You put an extra plus on the.
Thank you.
C++.
Yes, extra.
Extra plus.
There you go. I don't know how you like writing a code, so.
That's audio. You guys are good to go.
You know, sometimes it just doesn't work. Oh, I just choose a language. I tried teaching some kids with this, and it just didn't work.
Like now?
Better work than now. Why is it waiting for input? Okay, it just doesn't work.
Can you not just use like normal VS Code?
There's no VS Code in here.
Oh, just the official computer.
Yeah, it's official computer.
Sucks.
Okay.
Yay!
Let's look for alternatives. Use the guys one?
Yeah. No, just like look up use Oh, I see.
Real-time collaborative.
This is some crazy stuff. How did I not know about this? Create new file. Open ticket. Is this fine? This is fine, right? Okay. Let's do public. Private. This looks fine.
Do we need O2?
It's probably. Yo. Okay, let's test this out. Yo. Okay, use this. Okay.
That's
Okay,
crazy.
okay.
Innovation of the
Should we wait like 2 more minutes,
Yeah,
or
yeah,
will we
yeah,
start now?
No, we'll wait. Yeah, there's audio. They've been hearing all of this.
Yeah, yay!
There's audio on YouTube. You can hear it. Okay, good. Are we gonna get more attendance than this, or should we just start?
I mean, it's a fair amount. It's like
It's okay.
Yeah. Which ones? Ricky forgot. Oh, it was the traffic jam. Yeah, it was the goofy physics.
wait. Do you want to start attendance? I'll close the door.
Yep.
He never makes time for me.
Oh, you know, yeah. Oh, no, physics. So I have to do.
You can start any time, Austin.
Please scan the attendance form. So we spent a non-negligible amount of money on this particular event. Yeah, please scan it. We're testing out some new comestibles.
Comestibles.
Yeah, food. Does my mic have a furry thing on it?
Just like
Thank
ask
you.
one or two icebreaker questions, because otherwise it'll be a lot.
Yes. Yes.
Yay!
Yay.
I think we might have ordered too much food.
did AMI with like senior compass and stuff, but I jump shifted physics. I did it until grade 9, and then after grade 9, I was switched for the physics and the mathematics, so I didn't take it, which is very sad.
So I ordered like 3
Yes, but
That's fine. We're just six people out of 6 people out of budget. So how much is that? How many is that?
me and Susan were on the next.
That's 4 pizza. That's like alright.
Just bring them home to Jerry.
No, we're eating it.
Okay, fine. Yeah, let's start. Okay, so for this workshop, we're hoping to get you guys more like actually doing things. So the lecture portion of this workshop will be pretty short. The main point is that you guys actually get started on some problems. So this is the V-judge for today. It's probably worthwhile noting this down like via some like a more permanent system than this presentation that okay, great, excellent. Who is arriving?
internal. It's fine.
Great. Yeah, this is the V-judge for today. You guys can remember, it's only like what, 6 numbers. It's not that hard to remember, right? Like 802029. You can put it in your computers now. Yeah, the password's the same. It's always been. So
Might as well not even be there.
yeah, might as well not even be there, honestly. Yeah, probably get on this. If you're already confident with the content, today's content will be recursion and DP, mostly DP. If you already think you know some of the content, you can try some problems. Otherwise, you can listen in on the lecture, and afterwards there will be a more significant proportion of time allocated for you guys to spend on doing the problems. So this is the V-judge for today. All right, Susan, you can take over.
Okay,
Do you have your mic on? Yeah.
I do. We'll start off with a pretty simple problem to introduce the idea of recursion. This problem is called hallway tiling. So Austin has a hallway with dimensions 1 by n. He has 2 types of tiles. We have red square tiles and blue rectangular tiles. And the question asks, how many different ways can you tile the hallway? Here are some subtasks if you want to think about it. And I think, okay, so that's an example of how you would tile, of one way to tile a hallway of length 5. Do you guys want like 2 minutes to think about it? Or some of you look like you already know the answer. No?
Maybe give them like a minute.
Okay, you guys get a minute to think about this. And then we'll test you.
Do we use dynamic programming to solve the problem?
Okay, you made n 10 to the 9. Defeats the point of DP.
Wait, it's like... Oh, frig.
Yeah.
Okay, pretend that 9 is upside down and it's a 6.
You want the song? Okay.
I'm just gonna...
You can explain this.
I can explain it now.
Up to you.
Okay, I think that should be enough time to think about the problem. That is a 6 there, not a 9. Okay, so first of all, we can let a(n) be the solution for a 1 by n hallway. And if n is greater than 2 and we know the solution for like the 2 previous sizes, can we find a(n)? So we're just assuming that we already know the solution for 2 of the previous sizes. How would that affect our solution for a of n? Does anyone have any ideas? Yes, Austin?
You can add them together.
Whoa, really? Can we do that? That sounds a bit crazy. Okay, yeah, we can do that. So we have 2 choices for the last tile. It can either be blue or red, right? If it's blue, then that means we're adding like 2 tiles to the solution to n equals 4. If we choose it to be red, then we can just take the solution to n equals 5 and add 1 to it. Does this make sense? Hello. Is everyone fine with this? Welcome new people. Do you want me to explain the problem? Okay. Okay, sure. Yeah, so like as you see in the diagram, if we put like the last tile as a blue tile, the number of ways we can tile this just depends on how many ways we can tile n equals 4. If we put the last tile as red, the number of ways we can tile the rest is n equals 5, and we just add the 2. So we have the recurrence relation a n equals to a n minus 1 plus a n minus 2. That might look familiar to another sequence starting with f. Yay. Okay. Yeah, so to summarize, we simplified the problem by breaking it down into some subproblems. Right now, to calculate an, we need an minus 1, an minus 2. To calculate that, we need, I regret writing all of this, but basically, do we just keep recursing until we die? When do we stop?
I got the point.
Thank you.
Right?
Okay, so we can just stop at a equals 0 and a equals 1. Like, it doesn't really make sense to have a negative hallway size. Yeah, so these are our base cases. It's pretty easy to get the answer for this. Like, it's a pretty trivial subproblem. And from this, we can generate all the other ANs. So for example, to get A2, we can just add A0 and A1 together. Whoop. Yeah, so what's the solution for A0 and A1, guys?
0, 1.
Wait. I think it's 1 and 1. There's like one way you tile a 0 hallway, which is nothing. Yeah, so I'll go over some terminology. Recursion is when the function calls or depends on itself. So you can see like the definition for this function called a depends on itself. The base case is the simplest subproblem of the function. In our case, it is 0 and 1. The state is the variable that defines a subproblem. In our example, this would be n, which is the length of the hallway. And the transition is how the different states relate to each other. And in this case, it is the same relation we defined before. Okay. Before we go into the code demo, do we have any questions? No? You guys are very confident?
Press escape to escape the thing.
Great, thank you, Austin. Yeah, okay, we'll just do a quick demo on recursive functions.
Yes.
So for the program, I'll just take in a single number, which is the length of the hallway. And I will make the function a, as it is in the slides. And this should return answer a of n, right? And it's pretty easy to make a recursive function. All you do is you just call it again inside itself, and the relation is a n minus 1 plus a n minus 2.
Add a semicolon.
Okay, that was pretty easy. Does anyone see anything wrong with this example? Yay, everyone got it. There's no base case. If I run this code, it'll go forever until the computer kills itself. So let's include our base cases here. So if n is smaller than or equal to 1, you can just return 1. Okay, does that look a bit better? Are we confident now?
What if A happens to receive a negative value as an input?
I think
Although technically you would still return 1, isn't it? Not supposed to, except
n is bounded in the statement to not be.
Yeah. I mean, it doesn't make sense to have like a negative width length.
Do you have a question?
Question?
What if A is, what if N is really big? Won't you have a lot of calls?
Yeah, let's take a look. So if we run the code for 5, it prints 8. I think that's
correct.
That's correct, yeah. Let's try 500,000.
Gulp!
All right, so I might have just killed this IDE.
Okay. Oh, no, you can.
Oh, okay. Okay, so that's a funky looking error message. Basically, it means that like it called itself too many times, it died. So yeah, if we want to check what is like how the function is being run, I can just put a print statement here.
If you print, make sure to flush.
Flush.
Yeah, like endl.
Oh yeah. Okay.
Endl, because if you kill the program, like you won't, like no, there's no string. It's not a string. Yeah. Sure. Yeah. Try that.
Okay, so these are all the times the functions are called for. If I want to calculate the whole way of length 5, you can see it kind of there's a lot of calls basically, and you can imagine that as this number increases, the number of calls increases. Yep. Do you want to? Okay.
Yeah.
Actually, does anyone still need to look at the code?
Does everyone understand the code? Okay. So we're gonna do a bit better than
Do you have a question?
that. Oh, you have a question? Or do you want to look at the code?
Can I ask, like, what dynamic programming is?
Yes, we'll get to it.
Basically recursion?
Pretty much, yes.
I see. Thank you.
We'll get to it. Does anyone else have any questions about recursion? Okay. So we're gonna do a bit better than just that because clearly we put in like 500,000 and it didn't like hold in a reasonable time, right? So we want to do a bit better than that. So let's go back to this tiling hallways problem, right? And let's look at what the recursive calls look like. So this is an example where I've put n equals 4 here. And you can see in this example, n equals 4 is where I start recursing. And then I'm going to call n equals 2 and n equals 3 from those cases, right? And then from n equals 2, I'm going to call 1 and 0. At 3, I'm going to call 2 and 1. At 2, I'm going to call 1 and 0 again, right? And then these green cases are just like where it breaks, right? So does this diagram make sense to everyone? Because like I didn't want to draw it like a tree. Okay. Okay. So I was thinking, do I want to draw it like really nicely oriented? And I thought about it, and the answer was no. So I didn't do it like that. Does anyone have any further questions about this specific diagram? Huh?
Calculate the number of recursive calls you have based on your initial n.
Is there a way to calculate it?
Yeah. Like a specific formula. In this case, for Fibonacci.
I believe it also follows Fibonacci. Because think about it, like the amount of the way that I'd formulate this is there's no point having a whiteboard here because we don't even have a marker, right? But let Tn be the number of cores that it takes to compute an, right? Then Tn equals the number of cores to core n minus 1 plus the number of cores to core n minus 2, right? So it's just Fibonacci. Yeah? And Fibonacci is exponential in n, yeah?
If I think about it, I feel like it makes sense intuitively.
Yes?
Okay, sure.
Okay, Fibonacci is like, if you know the closed form, it's like phi to the n plus phi conj on root 5 or something, I don't know. Like it's on order exponential in n, right? Does that make sense to everyone? Yep, sure.
It just takes a long time.
Yes, it takes a while, right? Especially for n equals big, like 50,000 or 500,000. So let's look at this. Let's look at this diagram. What do we notice that's particularly bad about this diagram, or like what's apart from the fact that it doesn't look like a tree? Yep. Yes, exactly, right? For example, here, n equals 2, we repeat that, right? Like we've computed it here, but then we repeat it again here, right? We don't need to do all this work, right? So we can do a bit better. So the obvious problem is, why are we recomputing something like n equals 2 when we've already done so, right? In general, if maybe we didn't use 4, maybe we use k instead, this is what the tree would look like for n equals k, right? So k cause k minus 1 and k minus 2. And then k minus 2 cause like a bunch of crap, right? And then k minus 1 cause k minus 2 and k minus 3. And then k minus 2 also cause a bunch of the same crap, right? Because like, by our recursion, it's just going to recurse on k minus 2, k minus 4, etc., right? So it's going to do a bunch of the exact same thing. So we should not recompute the same thing again, right? Instead, we can just store the solution for each state after we've solved it. Yeah? So instead of recursing every time, we just store the solution every time we solve for it. So what it looks like is we remember the answer for each state in our recursion. And then when we recurse onto a state, we're going to first ask ourselves, firstly, is it a trivial case? Right? In this case, it would be like n equals 0 and n equals 1, right? Those are trivial cases. We can solve them in O of 1, sorry. And the second thing is, if it is not a trivial case, is it something which we've already solved, right? Have we already computed the answer for it? And if so, we can just recall the answer in O of 1, right? So we can recall it in constant time. Otherwise, we should just keep recursing. Yeah? Is it really that much better is the real question. So firstly, does everyone buy this approach, right? So instead of recursing onto every solution every time, we just grab the solution if we've already computed for it. Yeah? So is this really that much better? Let's test it, right? So here we have this really maintainable, excellent code from Susan. So firstly, I'm going to put this on the same line. Okay, so this is our recursive function at the moment, and we're just outputting the answer, right? So how about instead of just blindly calling the recursion, we store whether or not we've found an answer for it, right? And let's call this, wow, foreshadowing. We're going to call it like DP, okay? And DP is going to be a array, right? And so you guys are all familiar with C, I assume. I'll use C arrays, right? So this is an array of size max n, right? Which is like 1e5, so roughly 10 to the 5. And also, we're going to store whether or not we've seen the state, right? This is just for ease of computation, right? So inside our function, instead of returning this straight away, we're going to first ask, well, we're going to basically set our dpn to be the answer of this, right? And so what this will do is once it calls the two functions and computes them, it's going to take those answers and store them inside our array. Yes? And then since we've now computed the answer successfully for n, we will set viz to be 1. That means we've visited the state n. Yes? Does that make sense to everyone? And then we just simply return dp, right? So we basically store it in an array. We assert that it's being visited, and then we return this dp, right? Now, our two cases, every time we call this function, is firstly, if it's a trivial case, we should return an O of 1. And secondly, if it's already been visited, if viz of n, and viz of n is going to be 0 or 1. So if it's 1, this will return true. And then we will just return whatever we've already computed for that state. Does this code make sense to everyone? Yeah? And so now we're going to see out an, right, as usual. So if we print something like 5, firstly, we notice the answer is still correct, right? That's a good sign. That means we haven't screwed anything up drastically. Let's try like, I don't know, like 5,000 now. Okay. Okay, maybe I should have put it relative to a mod, right? Do you think int long long will fix it, or absolutely not?
Definitely not.
All right.
Maybe long.
There's no long long long. We will be using mods now. So let's take this mod 10 to the 9 plus 7. This is just like an arbitrary number, happens to be prime, by the way. like all we're doing is we are making sure that the thing doesn't overflow. So it's all good. This is gonna be fine, right? Okay, now it's going to work. So this looks probably correct, right? But the main important part is that this code successfully halts, right, in a reasonable amount of time, right? Compare that like to what Susan wrote previously. Excellent code style, by the way. But it didn't even halt, right? So she had to click the force quit button or like whatever error. I'll just do an error. Stack Overflow. Yeah, okay. So somehow it's better, right? It's faster and it's also more efficient in memory. So now we're going to ask ourselves what's going on, right?
Can you show what the output was again?
Huh? Sorry?
Can you show what the output was?
Are you gonna check it? It's modded.
It's modded. You need to take your take whatever Fibonacci thing is, chuck it in Maple, take it mod 189 plus 7, it'll probably be correct. I'm hoping. Really hoping. Good luck, anyone who wants to verify that. Okay, let's go back to looking at the time complexity, right? So this is the way that we measure how fast something runs. And so we want to analyze this algorithm and figure out how much faster it is, right? So we've already ascertained that the recursion is going to be exponential in n, right? Because it cores it cores pretty much equal to the Fibonacci number, right? So Fibonacci grows exponential in n. It's going to be O of something to the n. But how much faster is it if we just remember the states and don't recurse? Well, to analyze, consider the total amount of work that we do throughout the lifetime of the program, right? When we see a state for the first time, we're gonna perform some real computation, right? We're gonna grab an minus 1 and an minus 2, and then we're gonna add them together, right? And so this is O of 1 from the perspective of an. For more complex transitions, maybe O of n, O of log n, we know what transitions are, right? Like the state transition is the recurrence relation. For more complex transitions, it may be a bit harder to compute, but that's the transition complexity, right? Then every subsequent time we see a state, we just don't bother recursing in it again, right? We just grab it in O of 1. Yeah? And so since we meaningfully visit each state exactly once, our total time complexity is the number of states times the time to transition at each state, right? Every other time we visit in O of 1, right? It's trivial, right? All we care about is the number of states times the transition time. Yeah? Does this make sense to everyone from a broad perspective? If you guys do 2521, you might recognize this as DFS, but we won't talk about that for now. For our hallway tiling problem, we've improved from like IDK to the n, or some base, I don't know, I don't really care, right, to O of n, right? Because the transition time is O of 1, right? We're adding two numbers, and we've got n states, right, from 1 to n. Does that make sense? So our total time complexity is O of n, right? That's a lot better. And recursion combined with this idea of remembering what states we've computed is called dynamic programming, right? So that's all it is, right? Dynamic programming isn't some like fancy thing. It's just like you recurse and then you remember if you've done it before, so you just don't do it again. Yeah, and that's dynamic programming. Does that make sense to everyone? So there's an easier way to see why the complexity improves, and that's using like a different visualization, right? So since we only visit each state once, let's try visiting them in some specific order, right? And what does this order look like? If a state x depends on y, let's first solve y and then we solve x, right? So what this means is, for example, 3 depends on 2 and 1. So let's solve 2 and 1 before 3, yeah? And so for this hallway tiling problem, it will look like visiting 0 and then 1 and then 2 all the way up to n, yeah? In that order. Because 0 depends on nothing, 1 depends on nothing, 2 depends on 0 and 1, 3 depends on 2 and 1, etc., right? And so this order will make sure that we don't have any conflicts. We always compute everything before we need it. So all it looks like is we loop through the n elements and perform our transition exactly once. Yeah? And so what this looks like is, instead of, let's ditch the recursion. Huh?
Just leave it there, not close.
Okay. So some person has very annoying demands. Okay, so we're gonna read and out input n, right? And then I'm just gonna reuse the DP array here. What we're gonna do is we're gonna loop from 1 to n, right? Actually, we're gonna loop from 0 to n because 0 is a state. Yeah. And then if I is 0 or I is 1, then what should our answer be?
1.
Good work, right? It should be 1. Okay. And what about otherwise? If it's not that, what should we do?
Taking A of
A of I.
Is this for the same problem?
This is the same problem, yes.
So you just want to populate the DP array, right?
Yes, exactly, right? So in this case, our DPI will be DPI minus 1 plus DPI minus 2.
And not using A.
We're not using A because A is the recursive function. Yeah. Equivalently, we could have called this like solve or something, right? So we're not using our recursive function because we don't need to recurse, right? All we're doing is populating the DP array. Yeah. The reason why we don't use DP here, by the way, is because we need to compute those DPs first. So we need to call solve on them. Here, by the order of which we're doing things, we already computed everything before, so we can just grab it. Does that make sense? And so this, if we just, instead of scouting AN, if we just scout DPN, this should give an equivalent result up to mod, and I will add mod now. So, okay, let's take this modulo like some big number, right? Okay. What a great problem. Okay, and we should get the exact same number, right? Well done. So in this case, this is an equivalent formulation. Now it's very easy to see why it's O of 1n, right? Yes? DP array. Sorry, why do I not have to? Because they're in global scope, so they get auto initialized to 0. Apparently, I heard that the style guide for 1511 does not permit you to use global variables. Unlucky. If you want to reset them, you use like memset, right?
Dude, they don't know what that is.
What?
How many of us do you think we've actually done C++?
I don't know.
Hands up if you've done
C++ before. Okay, it's like a reasonable
hard.
number. Okay, if you guys don't like C++, it's very simple to convert this into C code, right? Firstly, you ditch all this crap, right? Secondly, you write, instead of cin, you write scanf, right? And then you I forgot how to do this. You do this or something. And then, thirdly, you ditch this and you write printf. And then it works in C, right? I'm not gonna write it. It's like the same code. Does everyone understand this? Yes. Does memset exist in C? I swear it does.
It does.
Yeah, it does, right? Okay.
How does malloc?
Calloc is the thing which sets it to 0.
How does that 0? Yeah.
That's for heap allocation.
Yes.
You want to allocate new method.
Yes. So does everyone understand this code as well, alongside the recursion as well? So there are two ways of doing this. This method is called tabulation, right? It's called DP via tabulation, or it's called bottom-up DP, because we're starting from the bottom and we're building up instead of recursing from the top, right? Yes?
Does all bottom-up DP not use recursion?
It does not use recursion.
Like, so it's done iteratively?
Yes, it's done iteratively.
Wait. I thought bottom up doesn't specify how the DP is done. It's just what direction it goes in.
Yeah. Like,
you can tell me a bottom up recursive DP in something wrong. And it's two different axes.
nah, it's really weird.
Wait, how bottom up recursive?
No, it's just the way that I thought about bottom up versus top down is top down you're pulling the states, bottom up you're pushing the states. No, it's the other way around. Bottom up you're pulling the states, top down you're pushing the states.
I feel like either can be done with either. So.
Not really. I guess just doing DP starting from n or starting from 0, right?
Yeah.
Okay. Does anyone have any questions about the tabulation or whatever that I just showed?
In what scenarios would reorder your performing the DP in manner?
No, it doesn't. It doesn't. As long as you perform it in an order that all the DP that you need is computed before you compute your current DP value, right? So for example, say you're computing AX, right? You need to have computed AX minus 1 and AX minus 2 first, right? It doesn't. If for example you wanted to make A0 your answer, and then instead of looking at n and then subtracting, you looked at I to n and then you added, that also works, right? It's also the same thing. Yeah?
Can you show me the proof again?
Yeah, sure.
Here. Okay.
The output.
The output's moderate. Yeah.
Huh? The output what?
The output's moderate, isn't it?
It's more.
Sorry, what? Can you explain again why did you use mode?
Because the Fibonacci grows really big really quickly, right?
see.
So for large values of n, it exceeds the integer thing, right? Cap.
see.
And so what happens is if you exceed that cap, it overflows, so it goes negative, right? Obviously there are no negative Fibonacci numbers, right? What I did was I just made sure it always stays within the integer thing by providing a mod, right? So this is not the exact Fibonacci number. This is the Fibonacci number mod 1e9 plus 7.
Oh, thank you.
Yeah?
So this is like obviously doing the recursive Fibonacci, but how come we're not using viz? Is this just an example where we're not doing that?
Yeah, we don't need viz because we're not the viz tells us whether or not we've seen a state.
Yeah.
Right? When we do tabulation, we know that we must have seen all the states before I. So when we're just looping from 0 to n, right?
Yeah.
So when we're doing tabulation, we know that we necessarily must have visited 0, 1, 2 before 3, right? Or like 0, 1, 2, 3, 4 before 5, right?
Yeah.
So there's no need for the viz array.
Yeah, I missed the.
Yeah. If you have the recursive thing, you do need a viz array because with recursion, it's not entirely clear what order you do them in, right? And so you'd like to know whether or not you've computed it so you can grab it back. Yeah?
Yeah.
Does that make sense to everyone? Yeah. This is basically a DFS, by the way, but don't worry about it.
Okay.
Yes. Okay, let's go back to presentation mode. Okay, well, when can we use DP? Well, DP is a subset of recursion, right? It's basically recursion, but you store the you store extra stuff, right? So we can use it when we can use recursion, right? For example, there's no weird cyclic dependencies, right? In particular, if you have an, it doesn't depend on itself, right? If the answer for some state depends on itself, you can't use recursion at all, right? So you can't even use DP. The second thing is it needs to be easy to define a state, right? If the state is really complicated, it becomes really hard to recurse over it. You can't recurse or you can't use recursion. And there are some nice recursive subproblems, right? I don't like, for example, in this case, it's really nice if we set it to be like, if we're able to solve the same problem, but just like smaller, right? In this case, we're solving the same problem, but our hallway is shorter by 1 or by 2, depending on whether we chose to put a 1 or 2 tile down, right? Now, additionally, the state also needs to be easy to store and reasonably sized, right? For instance, if our state when we're recursing is like an entire array, it's really hard to DP over that, right? We've got to basically map an array to an integer, right? Or whatever it is. So it's a bit annoying to DP over that. But if these things are true, we can just chuck like a DP state array over our recursion and we just steal the free optimization. Yeah? So that's what makes DP so funny. It's just like recursion, but you just make it better by storing the values that we've already computed. Does that make sense to everyone? Yes, okay. So you can also use DP to solve optimization problems. So far we've been looking at counting problems, right? Like how many ways are there to do X, Y, Z? We can also use it to solve optimization problems. And this is probably something which you haven't seen in 1081 or whatever. This is a problem called Froggy, right? There are n's, and it doesn't start with a frog, it starts with a bunch of stones, right? So there are n stones labeled from 1 to n, and the height of the ith stone is hi. Yes? So they're in a row from 1 to n, and then the height of the ith stone is hi. Froggy is initially on stone 1. It will repeat the following action to reach n, right? So if Froggy is on stone I, it will hop to a stone j, like between +1 to all the way up to +k. So what that looks like is basically it moves forward, right? Either like it moves forward by any jump from 1 to k. Yeah? So it's able to jump forward. That's the operation it's allowed to do, and it will keep doing that until it reaches n. Does that make sense? Does the frog? We're given k, by the way. K is like an integer we're given in input. Yeah. If Froggy changes height too much, it will get annoyed, right? So it starts off not annoyed, And the annoyance level increases by the absolute difference of the heights when you jump from I to j. Yeah? So the greater the difference of the heights, the more annoyance it will incur, right?
Does annoyance like stack up between?
Yes, it stacks. So like, for example, the first jump might incur 2 annoyance. The next jump incurs 4, so the total annoyance is 6. Yeah? Does that make sense to everyone?
That depends on height.
Depends on height, the difference of the heights, right? So if you start from I and you land at j, this is your annoyance level. Yeah? And my question is, what is the minimum possible annoyance of Froggy?
Does the jumping
Yes.
down decrease the annoyance?
No, it doesn't. It's absolute. So jumping down also increases your annoyance. So does this make sense, everyone?
Could you not argue annoyance is simply just what's the least possible height change from the point A to B? So the average of the least possible change in height made it whatever from.
Yeah, but it's like cumulative, right? Like even if they're at the same level, like he could be jumping around a lot to get there. You know?
Like for example, he might have to jump up, then down, then back to the same level.
Yes, yeah, that's why you take the accurate thing. Yeah.
And the other thing is that it can't jump all the way from 1 to n, right? It's got like a jump range. Like k is less than n, it won't be able to jump all the way to n. It will be forced to jump to some intermediary stones, right? Maybe k is big enough. Maybe it can jump from 1 to n. It can only jump forwards, yes. So does this question make sense to everyone? If I had a whiteboard marker, I would draw a diagram. Unfortunately, I do not have a whiteboard marker, so I will not be drawing a diagram.
Can you not use the like length limit over there?
Huh? Sorry?
Like
All the heights you need.
Wait, where are the markers?
The heights are not necessarily.
not
There are markers in the
markers.
thing behind you. Leave that.
No markers, unfortunately.
I'm gonna try my drawing tablet.
Nah, it's fine. I'll draw using mouse. Okay, so what this will look like is you have a bunch of height bars, right? Okay, like forgive my drawing. It's not the best, right? But I'm drawing with a mouse, okay? And then basically, this is Froggy, right? And Froggy starts on stone 1. And let's say k equals 2, right? If k equals 2, what this means is that Froggy can jump to either here or here. Yeah? And maybe let's say Froggy jumps to here. Then from this, and it incurs the cost, and the cost is the height difference between these two. Yeah? And maybe let's say Froggy decides from here, it's going to repeat the same thing. It's going to jump 2 this time instead of 1. And then it will incur this height difference. Yeah? And then finally, it will do a single jump here to get to here. Another possible route it could have taken is, for example, to jump from here to here, and then from here to here, right? There are many possible routes. It could jump here to here, like, I don't know, here to here, here to here. The point is, every time it lands on a tile, it will incur some annoyance. And your task is to find what is the minimum possible annoyance. So does everyone understand this problem now? Make sense? Yeah.
Okay, so one question is k fixed from the beginning?
Yes, k is fixed. Yes, we're given k in input. Thoughts? Oh yeah, these are the constraints, by the way. N is 10 to the 5, k is 10 to the 10 squared, which is 100. K. Thank you.
I mean, like for each, you could just go for each stone, compute like the minimum, like for each stone, go back k elements,
Yep.
find the minimum annoyance level,
Okay.
and then set that as, you know, set your current annoyance level at that index to that annoyance level plus.
Okay, that seems pretty good. What do you mean by minimum annoyance level?
Like, you would have been annoyed to get to a rock in the past, right?
Yes, exactly.
So yeah, find
Yeah.
the minimum rock.
Yep.
Rock with minimum annoyance.
So this problem seems to be solved recursively, right? So let's say Froggy is at n, then it could have come from anything k before it, right? Like from n minus k to n minus 1, right? Then we just need to find the minimum cost to get to any one of these x, right? And this is basically the same as solving as if it was getting to getting to n, right? It's not n, obviously, but it's like starting from 1, what's the minimum annoyance to get to some x? Yeah, and then like he said, we just need to take the minimum over all of those. Yeah, does that make sense? I'll show you what it looks like now. So what this looks like is, let's let dp of x be the minimum cost to get from 1 to x, right? That means we're basically solving the subproblem. Say the frog is starting at 1. What is the minimum annoyance for it to jump to x, which means it lands on x at the end? Yeah? Does this make sense, everyone? Yep. And so what our transition looks like is we look at all of the I between x minus k and x minus 1, so all of the I that it could have come from, and then we ask, what is the minimum of the annoyance to get to I plus the annoyance to jump from I to x? Yeah? And so what we're trying is we're trying every possibility where it could have come from, jumping from that location to x, to solve for x, right? So we're trying all the possible I that it could have come from, and we're going to test what is the minimum annoyance to get to I, and then plus what's the annoyance level to jump from I to x. Yep.
Would this only be could this only be done top down?
This can be done any way you want. I can show both implementations if you want. I'm planning to implement, unless you guys don't want me to implement. Okay. So does this transition make sense to everyone? So basically trying all the possible locations it could have jumped from, right, and taking the minimum score. Yep.
The next step, then they like I just solve I now, like DPI.
No, you don't have to. This is sufficient.
Okay.
Because all the I is less than x, you just have to recursively compute dp, right? Or like yes, I guess like yes, the next step is solve for I. You don't have to rearrange for I.
Yeah.
It's just like you just call solve I, right?
Yeah.
You basically say solve dpi now, yeah, and then this would continue recursively, yeah. And then so your base case is dpx equals 0 whenever x is less than or equal to 1, right? So if you jump negative or if you jump to 1, you have an annoyance of 0, right? Because it's no annoyance at all to jump from there to whatever. Technically, you shouldn't be, I should bound this at 0, but I mean, or 1, but it doesn't really matter. Right? I don't really care. I can do that. And so what's our answer? If we define this dp state, what would our answer be? How do we get the answer for this problem? Yep.
Can you explain why I is over there?
Wait, can I explain like why I is all the way over here?
Yeah.
Okay, so this basically means minimize with respect to a parameter I, and it means like I can take on any of these values. Yeah. So what this means is what is the minimum of this if I try all the I in this range, right? Over all the I in that range. Does that make sense? So I is like it's like a parameter which I introduced, right? This is like a new parameter, and what I say is, okay, what is the minimum of this value when I let I be any value from this range?
Mathematical representation of for loop.
Yeah, it's basically a for loop, right? So basically what I'm doing is I'm trying every I in this range. I'm saying what is the minimum of this over all the I that I'm trying? Because I can't try all the I.
Oh, I see.
Yeah, I can't try all the I because I can only get to x from k before, or like from 1 before, right? All the way up to from 1 before. So I can't try all the I. This just means I'm trying the I in this range, and then I'm trying to figure out what the minimum is.
So like you're doing 1 to I and then I to x, right? Like in there.
No, I'm doing basically what I'm doing is what this minimum does is it says like so let I be anything which is like where it could have come from. So what that means is, you know, the frog can only jump k distance. What that looks like is, well, I don't understand what you mean by from 1 to I and then from I to x.
Yeah, like that's like 1 to I, the minimum possible was DPI, right?
Yes.
And then like we're going I to x.
Yes,
that's
yes,
why we're
yes,
not
yes,
curving
yes,
GA.
yes. Okay, sorry. Like I don't know what you're sorry. Sorry, okay. Okay, so yes, that's what we're doing. As in here, that's what we're doing, right? That's not what we're doing here, but we're doing that inside the min. Basically, the minimum cost to get to I, and then to jump from I to x. Yeah. Does this make sense, everyone? Everyone have any qualms? Okay. And so our answer is simply dpn, right? I was going to ask you guys this, but it's fine, right? dpn is the basically the min cost to get from 1 to n, right? So that solves our problem. Yeah? And so now that we have a recursive formulation, we just chuck dp over it and we win, right? We chuck dp over it, and what's the time complexity of this algorithm if we put dp on it? Yeah, why?
Because we're looping once.
Yeah, pretty much, right? Or like, like it's not really ON. Okay, try again. Huh? Yeah, NK. Why?
There's an N and there's a K.
Yeah, correct. Okay. Or like more, I guess more formally, remember this formula number of states times transition time? It takes O of K to transition, right? Because we have K, okay, because we have K elements, right? And we need to grab from each of them. So it's O of K to perform a transition. And then there are N states, right? So it's O of NK, yeah? And okay, like I'll implement this, fine. Okay, so can I remove all of this?
Yeah.
Yep. Go.
I just have one question.
Yep.
If you went from the beginning and then looked like your window from the very beginning up to K and then picked the lowest and then kept doing that, would that also work? Or no?
I don't think a greedy works. Wait, you're thinking like basically pick, you start from 1, you look at a window of K, you pick the best and then you just keep going. I don't think that necessarily
Just
works.
show a count.
Yeah, can you come up with a count example?
Yeah, like I think the best option is you have to be like patient sometimes. You have to choose a bad jump and then you get good jumps.
Yeah, like okay. For example,
Patience isn't all patience.
okay, what's like a good counter example?
Put like a 1 there and then a 3 here. And then
Make them do this jump, I guess.
yeah.
Yeah. So let's say when K equals 3, and these are the heights, your froggy starts at height 1. If you were to look at K equals 2, it's better. Say that you were looking at what's the best jump that you can do from this scenario. Like you would pick 1, right? Because this incurs an annoyance of 0.
Isn't this fine?
Oh wait.
It needs to go back down.
It needs to go back down.
Wait, Austin, why don't you have like one that goes slightly down and the one that goes like up and then the same level again? Like
Okay, fine.
let's do like 3 3 1 5 5.
3
3 1 5 5. Oh, that works.
and then K equals 2, right?
I like you don't need the first 3, but yeah.
Just do one that's decreasing and it's going to pick the best up. It's going to be like.
Okay, you guys are great at coming up with counter examples. Yeah.
What do you want?
Looks like this. I'll type it on the whiteboard. So it looks like we set. Yes, I know. We set dp of x. dp of x is the we're computing for some specific value of x, and that is equal to the min over all I in the range from x minus k to x minus 1. And what it's going to minimize, it's going to minimize dp of I plus the absolute value of hi minus hx. Can we go back to coming up with a counter example?
Yeah.
You think this is fine? This is fine? Sure, I buy it.
Yeah.
Yeah, so in this case where k equals 2, sorry, k.
No, it needs to be
If you want to make it
6.
strictly better, you can make it like make 3 2, I think. That would work.
Make 3
Oh,
equal
yeah.
2. And then do we need another value here? Or?
Because like greedily you jump to 1.
True, okay, yeah. So say in this condition, say in this particular scenario, k equals 2, the frog can jump to here or here, yeah? And it pick 1 because that has the minimum cost. And then from here, you probably want to jump there. But this incurs a cost of 1 plus 4, yeah? The obvious better solution is you just jump to 5 and then you jump to 5. Yeah, and that will incur a...
So when you do it backwards, do you always guarantee that you're taking the right
We're not taking. It's sort of. It's more advanced than just going backwards. Because we're also computing. We're recursively computing the score to get to that cost in the first place, right? So if you look at what the transition looks like, there's this dpi in here, right? This is like a recursive call, and this means while we're going backwards, let's also compute the score that it takes to get to I. Yeah. Does this make sense, everyone? Yeah. Okay. So what does this look like? First, let's use global variables, and then let's make an array for heights, right? Let's assume we get our heights as an array. So what this will look like is we read in our n values into our heights array. I'm going to one index, which means the first value is at h1. And then, so what does this solve look like? Firstly, what are our base cases?
N equals 1.
Yeah, pretty much. N equals 1. Then we return, what should we return? 0, right? 0 is our minimum, our best annoyance to get from 1 to 1, right? Secondly, if we've already seen the state, we should just return k. Can we not make this n? Who decided to make this n? Okay, then we should return dpx, yeah? And then so now what are we going to do? We're going to perform our transition, right? So firstly, let's store like a running min, all right? And let's set this to some big number like mod. Mod is a pretty big number, yeah? And then we're going to loop through all I from x minus k, which I need to add k, by the way. And we're going to loop all the way from that to x minus 1. Yeah? And these are like all the i's, all the locations that we could have jumped from, right? I might read in k as well. Yeah? And then, firstly, if I is less than 1, so if I is less than 1, this is an invalid jump, right? Like this location doesn't exist, we should continue. Yeah? Otherwise, this location does exist, we need to store the min, right? So we're going to take the min as the min between itself and also dpi, or in case it's not dpi, it's going to be solve I, plus the absolute difference between the height I and the height x. Yeah? And so this is our recursion. What we're basically doing is we're looping through k elements, and we're basically grabbing what is the what's the minimum to get to that plus the jump, right? So basically we're trying every possible place that we could have come from. It's going to be the minimum to get to that location plus the jump to get from that to x, right? Which is what we're solving for. And then at the end, remember we need to set x to be visited, and we should just return dpx equals min, right? This basically returns dpx and sets it to min. Does that make sense? And it might help that before we run this, we make dp a bunch of really big values. Like this will do that. Don't worry about it. So now dp is a bunch of really big values, right? And so all we have to do now is we just solve for n, and we're done, right? So why not? Let's run this. Right? So in this case, n equals 4, k equals 2. We've got the heights. It looks like 2155. Right? In this case, the answer should be 3. I'm a genius. Okay, so does anyone have any further questions about this problem? Yes?
Why do you initialize dv to be infinity?
It doesn't matter.
It doesn't surely just keep it 0, right?
Okay, then okay, fine. I'm just being safe. What's wrong with being safe? It's like the same thing, right? Okay, so does anyone have any questions? Yeah, you guys can take a picture of the code. It's also on. It will be on the recording, the stream. Yeah, I am recording. It's on YouTube. So does anyone have any more questions about this video? Probably 0.
Exactly 6.
Okay, but people will come and look at it after, so we can. Okay, does anyone have any questions about this question? All right, I guess not. Matthew, over to you. I believe you have something interesting to say.
Wow, we're really going quickly.
We want to give them time to implement.
Matthew,
Oh yeah, take the mic. Whoa. Wait, these are like YouTuber mics.
Yeah. One goes on the inside.
Like this. Wait, this is fancy. Yeah, there you go. Hello. Wait, it's not louder.
It's only on the YouTube.
Yeah, it's only on the YouTube. It's only on the YouTube? Wait, how does that make sense? Like, the YouTube reads from this input. Ah, I see. I see. Okay, I thought my voice would get louder. Okay, so as the title suggests, we've been doing 1D DP so far. Basically, that means our DP array has only had one dimension. So if you look at Austin's code, for example, the DP array has always been one-dimensional with max n size. But we can do more than one dimension. How do I present again?
The 2 hours.
This one. Okay. So, just like last week, I flavored my own problem. Ain't no party like a DP party. Okay, so D-Pity is hosting one of his world-renowned DP parties, where people of all ages come together to solve some DP problems. The party, well, I mean, the whole thing is located in a grid, but the party is located at his mansion, which is at cell RC, which is the bottom right corner. You start in cell 1-1, which is the top left corner, and you can only move one down or one right in each step. Unfortunately, D-Pity is under investigation by the police. Therefore, some cells have police in them. So if Pij is equal to 1, that means that police are at cell Ij, and if you bump into the police at cell Ij, they're going to arrest you. So the question is, how many ways are there to reach D-Pity's mansion without running into police? If you guys are confused, there's an illustration on the next slide. So it doesn't. It's a very normal illustration. So you have a grid, right? The black cells means that there are police there. You can't go into them. Yeah, it's fine. That's your home cell, the top left corner. Bottom right corner is the mansion. And in total, in this case, there are 2 ways to get to the mansion. Right? You have to get funneled through that gap there, and you can have 2 choices at the end. So before we move on, does everybody understand the problem? Okay. So any ideas? You want to count the number of ways to reach the mansion?
Is that not just a maze solver?
Maze solver?
Kind of. It looks like a maze.
It's counting the number of ways, so it's not just trying to reach the.
Yeah. I think you can just calculate reaching with DFS, right? So you don't need. The question is, how many ways can I get there? There can be a lot of ways, especially if there's no police in the entire grid. Yep.
So I'm still using a viz array before. Do you have a value for like blocked pathway as well, like a -1, for example?
Yeah.
If you want to have values you've checked, values you have checked and successful, and then pathways you've checked and are unsuccessful, coming back to.
Unsuccessful, yeah. I think instead of sort of like checking if a pathway we've checked has been unsuccessful, we sort of like just don't visit the block cells, right? Like we'll never have a path that goes onto the block cells. So whenever we count the block cells, we just set that to 0. Like there are no ways to get to that, right?
Yeah.
So for example, I don't think the input is mean, but if the input somehow blocked off your home or the mansion, then you could just return 0. There's no ways to get there. So any ideas using DP? And I guess the hint is you might have more than one state. Or you might have more than one variable in your state.
I'm
Yep.
not sure if this exactly works, but if you know you can get from, if you start at the mansion,
Yep.
and then you see if you can get to that cell somehow, then you check the previous, like if you know you can get to a certain cell, then you know the number of ways. Oh, it's number of ways that matter.
I think you're on the right track.
Wait, what's the problem asking? Is it number of ways to get to?
Number of ways to get to the mansion, yeah. Yep.
So the only way to get to a cell is
either to go from the left or go from the top.
Yep.
And those are both mutually exclusive and like exhaustive.
Yes, sure.
So you can just add up the ways to get to the cell above or the cell to the left.
Yep. So basically, the observation is like, just think of any cell on our grid, like let's say this cell. If we're at this cell, we know that we must have either come from the left cell or the cell above it in the previous move, right? Because we can only move right and down, there are only two options of where we could have been. So if we add the number of ways we could have gotten to the left cell and the number of ways we could have gotten to the top cell, that should be the total number of ways to get to the mansion. I think implied in that sort of definition is that our state needs to be, the main part of our state needs to be which cell we're on. And we probably need more than one variable to store that. So the idea behind this is that instead of doing how many ways are there to get to, dp of I, we want to find how many ways are there to get to dp of ij. And there's no reason why we can't make the dp array 2D. So our dp array could now be dp of ij is the number of ways to get from our home to cell ij for every cell. And just like we said here, to transition, we can either go from the cell above us or the cell left of us. However, there is a special case, which is when there's police at a cell. And as we said, if there's police at a cell, there's 0 ways we should end up at that cell. We should never go there. What are our base cases in this problem?
When we start from the mansion?
Yes, we start from home, not the mansion, but yes. There's exactly one way to start at our home, right? So dp of 1, 1 is equal to 1. Okay. I think the last question is, what is the time complexity of this solution? And we can remember Austin's formula, which is how many states do you have, and then how long does your transition take? You can multiply them together. Any ideas? How many, yep. How many states do we have in this case? dp ij. Yeah.
R times C?
Oh yeah, r times c, n times n. Yeah, same thing. Like the number of cells in the grid, right? So we have O of rc states, or n squared, same thing. And how long does our transition take? How long does that formula take to compute in our code? Just to compute like dp of I minus 1j plus dp of ij minus 1.
Would it be O of 1 because you already have it?
It's O of 1 because you already have those values. The transition is just how long does it take to evaluate that formula, right? You can assume that you already have all the dp values. So there's O of rc states and there's O of 1 transition time. So the time complexity is O of rc in total. So generally, if you see a problem statement with like 1,000 to 1,000, that's probably okay. Next problem is a challenge problem. I'll give you guys more time to think about this one. So next problem is called Pity's problems. Apart from the police, D. Pity has another issue. He needs to pick problems for his party tonight. Specifically, you have n problems, and each of them have a unique difficulty level, right? He wants his problem set to cater to all ages and skill levels. So he needs to choose problems which are equally spaced in difficulty. It's like in an exam, you can't have all the problems really hard, all the problems really easy. They need to be spaced apart, It should ramp up slowly.
Ages and skill level is unique.
Sorry?
Ages unique from skill level.
You could have like a really cracked baby. There's nothing wrong with that.
Wow.
What?
Okay.
So the question is, help him find the biggest possible size under this restriction. And there are two subtasks.
The first one is if n is 1,000 and d is 10,000. Second subtask, what if d is really big? Just to illustrate the problem statement, there's a sample case on the next slide. So what this means is that n is equal to 8. There are 8 problems, and these are their difficulty levels. So does anyone know what is the largest possible problem set we could pick if all their difficulty levels are equally spaced apart? Just for the sample case. Like the answer is 4, it's up there, but which set corresponds to that 4? Yep.
Is it 1, 4, 7, and 10?
Well spotted. 1, 4, 7, and 10. So we can pick 4 problems, and each consecutive problem differs by 3. So that means that the biggest problem set we can pick is size 4. You never have to worry about like problems of the same difficulty, because I think we specified that all problems have different difficulty levels, and you're given them in ascending order. So, any ideas for the first subtask? Yep.
Brute force every mod.
Brute force every mod?
Yeah, so if you go back to your sample case, 1, 4, 7, and 10 are all 1 mod 3.
Yeah.
So you just say for every mod you just find like which thing has the most occurrences.
I don't think it's just most occurrences, because like imagine 7 wasn't there, right? 1, 4, and 10 are all 1, but you can't form size 3 problem set because they have to be next to each other. Yep.
Recurs like biggest possible size until like I element.
Yep.
And then compute the difference.
So I think I actually have that on the next slide. So is your idea something like dp of I is like the biggest, yeah, the max length of the problem set ending at I? Okay, this is like a really natural first idea. I think you pointed out, how do we know, like how do we find the difficulty spacing between the problems in this dp state? It's a bit unclear what we're going to transition onto from dp of I. I think the hint is that in the first subtask, d is pretty small. D is 10,000. So O of nd, for example, would be perfectly fine.
Like computing the difference between first one and then ith one.
First one and then ith one. You don't have to necessarily have the first element in your problem set. It can be any problems, any set of problems is valid. So the problem with dp of I is that it's not obvious what our previous element was, right? Because let's just say in this example, if dp of I is on the element 10, we don't know whether our previous element should be 9 or 4. And more importantly, once we pick the previous element, we have no way to tell our future dp state this spacing should be the one that you use, right? So we need a way to add information to our state. We need to add the spacing between elements into our state, right? And using 2D dp, we are able to do that. So we can just add another variable to our state, which is it ends at I, and the spacing between problems is S, difficulty S, right? Because this means that we know exactly what we want to transition onto. So from this state, we only want to transition to the previous problem if the difference between the previous problem and the current problem is exactly S, right? Does this make sense? This transition?
Well, I think
So,
it's better if you give like an example of what
sure.
dp I don't know, like, for example, say we're trying to compute like DP3, right? Which means the last problem that we pick needs to be a 4. And then the question is, well, what's like, we could have a bunch of different like sequences which end at 4, right? You could have like 1 and 4, you could have like 3 and 4, or you could just have 4, right? And so the way that we encode that is through a different state. So for example, like let's say DP4, 1. That means or like 3, 1, sorry. What that means is what's the maximum problem set size that you can pick if you end at this third element, which is 4, and your gap is 1 between each successive element. And so in this case, that would be 2, right? Picking 3 and picking 4. If it was, for example, 3, 2, which means the gap size needs to be 2, there are no solutions. So the best you can do is just pick itself, right? And so the answer would be 1. And for example, if it was 3, it would also be 2, right? As in 3, 3, because it means you pick the third element and the successive spacing is 3, right? And that would look like 4 and 1 picked together. So the answer would be 2 for that DP.
Yep. So the spacing sort of tells you what you need to transition to, right? You should only transition to a J if the difference is exactly that S value. And as Austin said, our base case should just be, well, if we can't transition onto any J, just set dp of is as 1. The only problem set that we can pick is just that element by itself. So now's the big question. What's the time complexity? Yes?
What are the bounds for J?
The bounds for J? J is just another index in our problem set. So J can be anywhere from 1 to n.
1 to I, right?
Oh, yeah, 1 to I, but as in like it's O of n. So the question is, what is the time complexity of this solution? How many states are there? Well, how many I values are there? There are n possible indexes, right, for the I value?
N plus 3?
Hmm?
What did you say?
Possible.
N possible, yeah.
N possible.
There are n possible values for I.
N possible
I thought like N plus something.
There are n possible, O of n possible values, I mean literally n possible values for I. And for S, well, you could try every spacing. And in total, I think we had D being our total distance. So there are D possible values for S. Because our transition is only O of 1, it's just one formula, our total time complexity is O of ND, right? And this passes subtask 1 because in subtask 1, D is pretty small.
You can find the J quickly using any means that you have. Like, I don't know, like maybe you chuck everything.
If you want to be good, you can use a hash map, but you can just use an array, like a C array, it's fine. So now the question is, how do we optimize this algorithm? So it's still a DP, but we want to reduce the size of our D state. If you remember for the second subtask, D is a very big number. D is like 10 million. You can't have that in this state. Yes?
So you subtract the final value minus first value? No?
Can you explain what you mean?
No. I mean, it's ordered, right?
Yes,
so
it's ordered.
So if we take the last one and then first one and then subtract them, then the difference is possibly smaller than the D? No? Is it
If you
the
take
same?
If you take the last one and the first one, and then the last problem in your set and the first problem in your set?
And divide.
I think the issue is that you need like every spacing to be the same. So I can't just have like the n spacing be like every spacing in the thing has to be the same. Like 1, 4, 7, 10, each of them are exactly 3 apart. So it's very similar, like the hint is it's very similar to this, except our second state in this algorithm is S, right? And S can be really big. S can be like O of D. And D is 10 million. So the question is, are all spacings really possible? Do we need to evaluate all S? And if not, how can we reduce the number of S's we try?
Complete difference every time,
Say it again? No, just say it again. I couldn't hear you.
What about calculating difference every time we input the array?
Calculating the difference every time we calculate our DP?
Every time you input the array, like when you read in the array, you calculate the difference.
The difference between every consecutive element?
I don't know.
I don't know.
So,
Like sort of like that.
By the way, if this problem's too hard, you can feel free to try the easier problems on VJudge. I guarantee you they're easier than this problem. This problem is quite hard.
this is a challenge problem. Let's give an example. So, okay, have a look at our sample case. Let's say that I is 6 and that's the problem with difficulty 10. Which spacings are possible if this was our last element in our problem set? Like, assuming that we want our problem set to be at least size 2, which spacings are possible?
Like the number can divide 10? No?
It doesn't have to divide 10, because it just has to be the difference between 10 and one of these elements. So it could be 1, for example, 10 minus 9, right? It could be 3, 10 minus 7. It could be 6. So how many differences are actually possible if our last element is 10? I? Did you say I?
3?
3? Well, I mean, this could, 1 is an option, right? This could be the difference.
And
This
3 and 6.
3 and then 6, yeah, and then 7, and then so yeah, I minus 1, yeah. So if we're at position I, there are only I minus 1 differences that are possible because we must have come from one of the previous elements, right? In general, let's just say that there are like only O of n differences possible. So what that means is that our S state here is way too big, right? If this state is 10 million, we don't need it to be 10 million. It can be O of n. So the key to our second problem is let's change our state, right? For some I, we should only consider a value of S if there's some J such that the difference is S. In other words, there are only I minus 1 possible S's, right? So by making this a part of our state, we can just set dp of ij being the max length of a problem set with the last problem as I and the second last problem as j. That's equivalent to just having the valid s's, right? So now the transitions are exactly the same, right? You transition to some k such that that's true, but the size of our dp is smaller. And specifically in this case, what is the size of our new dp?
N squared?
It is n squared. Very good. N squared. So this works because in the problem statement, n was like 1,000, so n squared passes. But anything with d in it is a bit too big. So, yeah. Okay. Any questions about this problem, by the way? It's a very hard problem. I don't think this problem is on VJudge. It's on ORAC.
It's on ORAC.
ORAC is the Australian Informatics training site, but we can link this problem to you guys if you want to try it out. All right. I think that's the end of the slides, right? So feedback form.
I mean, okay, workshop's not over. You guys have to do problems. Unlucky, right? Okay, so the idea is like probably all get on VJudge, try some problems. The first, it should be in roughly difficulty order, I believe. You guys can fill out the feedback form regarding the actual, like the lecture. Also fill out the attendance form if you haven't already. That way we can hopefully get food to you guys. If the place that we're ordering from doesn't take 6 years to prepare the food, we will get food. And yeah, otherwise get on VJudge. The code is 80209.
It's on the next
029.
oh, no,
it's not on the next slide.
Oh, yeah.
Okay,
No, you trust me.
Okay.
See?
It's 802029. Like I said, it's only 6 digits. It's not that hard to remember.
Where's your I love CP stickers?
There's no I love CP stickers. Okay. Class adjourned. Bye. Bye stream. Wait, how does this work? Do I just stop streaming?
So tough. Press stop streaming, you know?
Wait, like I just press end stream, right?
Yeah. Why is it like 10 seconds behind?
Yeah, I don't know.
Oh, 32 views.